Yeah, perfect. All right, thank you. Okay, so I guess the main reasons of why one should study complex analysis, I guess, are twofold. Right, one is that it's just a very nice theory. You'll see it's just a really beautiful mathematical theory. And I'll try to convey today why that's the case, what makes it a very nice theory, and sort of very fundamental theory. The other reason it has many applications. And what I mean by this, I mean both inside math and outside math. We'll focus more on the theory and applications within math, but I will spend a bit of time today just sort of intuitively trying to convey why it is that it actually shows up quite a bit outside of math. It will show up it's a very natural context to look into things like differential equations, into signal processing, control theory, a bunch of stuff. Very naturally uses complex analysis, and I'll try to sort of explain why that's the case. Okay. Yeah, so I will. I can. The notes that I write, I can scan them for sure. Okay. So my account is licensed, which is being the host. But the problem is that I have this limit at 300 that I don't have over webinars. But for This Is Better meeting, and I completely forgot that the meetings had a limit because I never even reached close to it. But this will be fixed by Friday. Okay. And the applications in math, I guess the best. There's a famous quote by Adamard that he says. So I'll read the quote to make sure I quote it correctly. The shortest path between two truths in the real domain passes through the complex domain, right? And this is really, it's exactly what makes it so important in math. Is that many times when you want to understand mathematical objects that have nothing to do with complex numbers, actually, very, very often, the proofs or the arguments go much, much faster if they go through complex analysis. And there's some results even that we don't know how to do them, not going through complex analysis. Okay, and so what is complex analysis? What are we going to study? Right, we'll study the complex numbers. And so the best way to think of this is that, we start with the natural numbers, which, some people include 0, some people don't. I want to get into that discussion. Right, they're just the positive integers or the non-negative integers. Right, these are sort of the first, the most natural numbers, the first to be invented. But then you can ask, very naturally and very early on, people ask themselves, okay, what if I want to have a solution to x plus 1 equals 0? How do I solve a problem like this? Right, clearly I cannot with just these numbers, and so it makes a lot of sense to consider also negative numbers, right? The answer to this, if I want to solve questions of this type, then I have to start taking the integers. So then I allow now negative numbers. But of course, the story, as you know, doesn't end here. And you might want to solve equations of this type. How do you make sense of something, the double of something being 1? Of course, you cannot make sense of it in the naturals or in the integers. So you need the rational numbers. And so these are all fractions of integers. Okay, but still, this is not quite, there's equations that you can solve here. For example, if I write something like, what if I want to solve x squared equals 2? How do I solve this? Well, this doesn't have a solution over the rationals. Although this goes back to ancient Greece. It's not, it's not trivial to prove, but probably you've seen this proof before. And so for this, you need to go into the real numbers. maybe this is not the most natural way of motivating the real numbers. Maybe the most natural way is that you want something where, every Cauchy sequence is convergent or something like this, or you want to have a nice metric space, something like that, and that's really maybe the right way of motivating the reals. But okay, let me motivate it as just having solutions to equations that you couldn't make sense of before. But even in the reals, there's still equations that you can't make sense of. They don't have solutions. So in particular, if I want to solve x squared plus 1 equals 0, not completely, right? This doesn't have a solution over the reals, right? So if x is a real, x squared is always in the negative, right? And so it cannot possibly solve this equation, right? So how do we make sense of this equation? Well, this equation is made sense in the complex numbers. And I'll try to write bigger. Is now better? The board had some water over there, so now hopefully you can read better. Yeah, and I'll try to write bigger letters. Okay, so the complex numbers start with, one can define them by just wanting to solve this equation and saying, okay, I'm going to define the solution to this equation as a number. And I'm going to define a number I, whose square is equal to -1. Right? Another way that we think of this, that probably you've seen in high school, is that you can just take I to be the square root of -1. Right? We define this new number that makes absolutely no sense over the reals, but we define it nonetheless. And now the complex numbers, right, are just the numbers that whose reals plus a multiple of I. Right? So they're all numbers A plus IB, where A and B. And so this is why, because this sort of looks a lot like R2, that's why we tend to call this the complex plane. Okay, so let me clean the board. So we have the complex numbers. Okay, that we often call the complex plane. Now, sort of the amazing thing, or the remarkable thing, what really makes, part of what makes the theory so nice is that this story of, okay, if we can't solve something, let's just create other numbers until we can do whatever we want. This sort of ends here, right? The extending, maybe. This is an extremely hand-wavy statement, but extending sort of ends here. Right? And this set of numbers will in itself, you can solve most equations that you can write. Okay, and we'll see. I'm not yet saying anything very precisely, but you'll see in a second what I mean. Okay, and so this is sort of really the natural extension of the natural numbers in a way, right? If you go and try to solve more and more an equation, you get here, and then here you sort of stop. And this is what makes them so fundamental. Okay. And so, I mean, I guess another way to say this is, can we try to write equations that cannot be solved here, right? All we did, we just found an equation which was x squared equals minus 1, and we said, okay, we want to be able to solve that. And we came up, we created a number to solve that, but now we created those numbers, maybe with those numbers we can write equations that we can solve, right? And so in particular, what about if I do say x squared equals I, right? Or I take, the negative fifth root of 73 or something like this, right? But let's say I created this new fancy number I, and now I want to solve the equation x squared equals I. Right? Do I need to create another number j, which is the solution to this? And then maybe if I put j here, I need to create another number k, right? I mean, we could spend a long, long time trying to extend numbers this way, right? So the point is that this is not the case, right? The complex numbers will already have solutions to this. And okay, I'll write the solution, and it will seem like it will come just how I have. But very soon you'll see exactly how I do this. Right? So if I take the square of this number, so I take 1 over square root 2 plus 1 over square root 2 times I, right? So this is a complex number. And if I take the square of this, okay, so we'll see complex numbers should satisfy, the distributivity property and all the nice properties that allows us to make calculations with the reals. Okay, so the square is just the square of this, plus twice the product of this, right? 1 over 2 times 1 over 2 is 1/2 times I, plus the square of this. But the square of this is just 1/2 minus 1. Right, so this cancels, I get I minus 1/2. Right, and this is equal to 5. Okay, so I didn't just show you that you can do all the equations this way, right? But at least, this would be a good attempt to try to create a problem, and it's not a problem. We can actually solve it, right? You can ask, how did I do this? It'll be very clear how this is done a bit later. And more naturally, now you can ask the question, and the very natural question after you see this is, okay, you picked a very simple equation, but what if I give you a more complicated one? Right, and you can ask, do all okay, so I can ask, do all polynomials over C have zeros? Right, so do all polynomials whose coefficients are complex numbers, do they all have zeros? Right, I mean, I wrote this equation this way, but I could have written it like this. Right, so a polynomial equation having a solution is just the same thing as another polynomial having a zero. Right, so now I can ask this question. Right, this is definitely not true over the reals, right? X squared plus 1 has no zeros. Okay. This is also not quite true as stated, because the polynomial P of z. So usually we use the same way that we use x for real numbers. We use z for complex numbers a lot. The polynomial just equal to 1 constant, of course, doesn't have a zero. Right? It's not even something that really makes much sense. Right? The constant polynomial, of course, will not have a zero, but we can ask this question for the interesting ones. Do all non-constant polynomials over C have zeros? Okay, it turns out that the answer is yes. This is known as the fundamental theorem. So take a few seconds to sort of think about this from the more philosophical viewpoint. All we did was we fixed one hole, right? Over the reals, there were there's many polynomials, of course, that have no zeros. All we did was we fixed one hole, right? We just created a number to solve one polynomial equation. And oftentimes, when you fix a hole, another one shows up, because now we're even introducing new numbers. So we've been introducing new polynomials. Right? It's not only that we might have to create many numbers for there to be solutions over all polynomials over the real, but by creating these numbers, we're even making this statement harder, right? Because now the polynomials themselves can have complex coefficients. But somehow this is really the closure of all of this, because now all polynomials will have zeros, right? And this will have a lot of implications, right? Studying solutions of polynomials will be much easier. And more importantly, there's countless things, both in math, in physics, in signal processing, in trying to understand differential equations, control theory, things of this type, where eigenvalues of matrices are extremely important, or diagonalizing operators, or things like this. But if you think about what is an eigenvalue, right? An eigenvalue is just a solution to, right? It's just a solution to some polynomial equation, right? The characteristic polynomial. And so over the complex numbers, all these polynomials will have solutions, right? So the spectral theory will be much, much richer and much, much simpler, much nicer. And this is one of the reasons why it's so useful to think in terms of complex numbers, is because matrices and the spectral theory of matrices over complex numbers is just so much nicer, right? Because matrices have complex valued eigenvalues, even if their entries are not complex valued. Okay, so I guess I'll try to motivate, like, even further this. Okay, so complex things over the complex plane will have, basically there's two very important properties. And in a way, almost all the implications and the results and so on can be traced back to one of these properties. And so one is the fact that all polynomials have solutions, right? We say that the field, the complex numbers, is algebraically closed, right? Any algebraic equation, you can solve it. And the fact that it's algebraically closed will have, will make it the right tool, for example, to do algebraic geometry over. If you want to study algebraic variety, so solutions of polynomial equations, it's much more natural to do it over the complex numbers. And algebraic geometry certainly is much, much nicer and is done almost essentially over the complex numbers. Doing spectral theory, right? So diagonalizing matrices or operators, or taking eigenvalues and eigenvectors of matrices is also much nicer over the complex numbers. This is also a natural place to look at many differential equations. Right? The reason is that, and this will be more apparent later on. I mean, today all I'm doing is I'm sort of trying to go over the whole course in one lecture, just to sort of explain intuitively what is going to happen and why things are important and so on. Right? So it's okay. I'm not being very precise at all. I'm packing all of one semester in one lecture just to give you an overview. But the reason why it's important over differential equations is you can view many differential equations as just finding some eigenvector and eigenvalues of differential operators. Right? Many differential equations, at the end of the day, you're trying to find some kind of eigenfunction or solving some kind of eigenvalue, eigenvector problem. Right? And so because these problems are much nicer over the complex numbers, you can actually do oftentimes a lot more over the complex numbers. And in particular, and I'll say a bit more about this in a bit, certain physical differential equations appear to have very different behavior over the reals, right? If you take some kind of like heat diffusion type thing, you might see some exponential decays of solutions and things of that type. Many other equations will have, some kind of oscillatory behavior, like some kind of wave, right? And having some kind of sine or cosine, so some kind of wave type pattern on a solution of a differential equation or a physical process, feels very, very different from some kind of exponential decay that you might see, right? But they're both sort of very physical type processes. But actually, over the complex numbers, this comes exactly from the same function. Because over the complex numbers, the exponential function, when looked in the real direction, will behave like how the exponential that we know and love, but over the imaginary axis, it will behave oscillatorily. And so really, it sort of puts waves and diffusion and so on a bit in the same ground. And and so again, a bit inside the spectral theory, it's also how things like Fourier analysis. You can think of Fourier analysis as showing up this way. I don't know how many of you have seen Fourier transforms and Fourier series and Fourier analysis, but you can just think of Fourier analysis as trying to find, again, eigenfunctions, eigenvalues, or diagonalizing operators. And in this case, usually it's a translation operator. Right? And so if you try to do this, because over the complex number is much more natural, they sort of recover Fourier analysis. Another place where it shows up a lot is control theory. So control theory, for those of you that don't know what it is, control theory is basically, we can think of robots, right? So you want to control some system, usually a physical system, but I guess it doesn't need to be physical. And it has some kind of input that you can give it, and the system behaves in a certain way, right? Maybe the best way to think about it is some kind of robot. And you want the robot to stay still, and all you can do is maybe move the hands of the robot, and there's some, wind or some perturbation or something like this, and so the robot, as it's falling to one side, needs to sort of open the hand to move on a bit to the other, right? And these are the typical control problems. So when you see like a robot walking, or like a robotic arm, balancing something up or something, this is a control problem that's being solved in the back, right? And there's some kind of input that's given to the system depending on its state, and you want it to be stable in some form. But if you think, now I'll be extremely, extremely end wavy. But if you think of what's being, the feedback or the input that you're giving to the system, if you think of some kind of linear operator, some matrix that you keep hitting on the system, then you might hit the matrix A, and then when you hit it again, you might get something like A square, A cube, and so on and so forth. And so understanding if these things are stable or not, it's sort of intuitive that it will have to do with eigenvalues, and especially eigenvalues of these matrices. And in particular, what will happen is that the matrix exponential will play a big role. And so you will have to understand the real parts of eigenvalues of these matrices associated with these control problems. And this essentially is always done over with complex analysis, because these matrices do have complex values, eigenvalues, and what we're interested in is the real part of them. And so you have to study sort of the behavior of the eigenvalues over the complex plane. And so this plays a huge role in, say, robotics, for example. Another place this plays a huge role, and I mean a bit because of maybe Fourier analysis, is in signal processing. Right? When we think about signals like Wi-Fi or some kind of wireless signal, but it doesn't need to be wireless, then complex analysis is sort of the natural language to talk about signals. One way to view this is that they are right. Signals oftentimes are some kind of oscillatory type behavior, some wave, right, some sine or cosine or something like this. And it's this, the fact that sine or cosines will be very related to the exponential that will make studying this with complex analysis a lot nicer. Maybe I should draw a little picture. Maybe I'll draw the little picture a bit later. let's just leave it at that, and I'll draw the signal processing picture a bit later if we have time. Okay? Let me erase this side.
Someone has a question. Raise your hand.
Yeah, go ahead.
Whoever it was, can you raise your hand again?
It's fine. I was testing out the feature.
Could you go ahead again? I didn't have this loud enough.
It is fine. I was just seeing if it worked for me.
Ah, perfect. Thank you for testing. Yeah. All right. Great. I'm glad this works. Okay. Or no? Can you hear me? I saw it was
now we can hear you.
Okay, perfect. Sorry. Okay, since there's like 7 minutes until the break, then I'll actually draw the signal processing picture before I go into the other important property. Okay, so one way, I mean, again, right? Today's lecture is extremely hand wavy, and I just want to sort of get you curious and excited about complex analysis. But if you think, and so, take all of this with a grain of salt, because to actually explain the applications, we might do this a bit in the end, but it would take, take a lot more effort than just a 5-minute picture, but I'll do the best I can in 5 minutes. But if you think of, some kind of signal, like think of some signal like this, right? You see some signal, some wave. It's not clearly this wave has sort of two components, right? It's some kind of oscillatory behavior, right? But it also has some kind of amplitude that is much bigger here than here. But if this is 0 and you say, well, the amplitude is sort of the size of the signal, then the signal here has much size as it has there. But clearly, the amplitude of the wave here is different. So it's not completely obvious how to make sense of how to sort of split up the wave in a way that you can understand, right? How to measure the size of it and so on. It's not completely obvious. You could, of course, say, okay, take the maximum in an interval around, but it starts being clunky if you start doing things like this. It's not quite clear that there's a fundamental way of doing it. But one way in which you could make a lot of sense out of this is to think of the wave as instead of point in 2 dimensions, right? That's moving, right? The curve in 2 dimensions that may be moving, and then it moves a bit on the inside, something like this, right? So this is a curve I'm following, and then I take the real part, right? So what I mean by this is I'm drawing, right, the same way that the complex numbers, and we'll go over this a bit more carefully, for sure, on Friday. But I can think of the complex numbers as pairs of integers, and so I can write them here. This can be my A, and this can be my B, right? This can be my real part and my imaginary part. And now, but here it doesn't even matter really that they're complex numbers or not, but you can think of some kind of curve in R2 that's going around. And if you project, right, at each point you project what it is on the real axis, you get exactly something like this, right? I mean, another way to think about this is if you're rotating at an angle theta, right, the real part is exactly cosine of theta times whatever amplitude you have, so whatever radius you have, right? And so if I think of a point going around or an angle, then if I look at what the projection on the x-axis or the real part looks like, then I start getting something that looks a lot like a wave, right? But now here, it's very easy to make sense of when is it that, which part is the oscillatory part and which part is actually the size, right? Because the oscillatory part will be given by some kind of angle, and the size will be given by some kind of radius or amplitude, depending which community you come from. Okay? And so this, even without mentioning complex numbers at all, right? This already seems to make, to potentially be quite useful to represent things like signals or waves or things like this. Okay? And it turns out that this is exactly what the exponential is doing. Okay, so right, and this is the famous Euler formula, which we'll establish. Euler's formula is one of these things where every book, like, it satisfies, say, 4 very nice properties. You can define it because of one of the properties it satisfies and then prove the other 3. And I think the 4 books I looked at, they all pick a different one for which one to be the definition. But right, the exponential of I theta is cosine. And so, which is exactly this picture. Going around is just taking an exponential, right? The same way that you can see the exponential decays and all those things as the exponential, right? E to something. Here you can see this oscillatory behavior as well, because when I take exponential of an image of I times something else, right? So a purely imaginary number, then I get exactly this type of behavior where the real part is some kind of wave, oscillatory thing. So is the complex part. And this will play a huge role. And now you can imagine how this will be the solution to many differential equations, right? Because the exponential is its own derivative and so on and so forth, right? And so we'll go through this, a lot more carefully when we actually start the proper material on Friday. But just to already give you a hint of what is going on, why it would make sense to do this, to do signal processing with this language. And that's also why Fourier analysis is all in terms of exponentials of e to the I something and so on. Okay, so we'll take a break, and then we'll come back 15 minutes. I'll see if I can get the limit taken out in this 15 minutes. Seems a little hard, but I'll try. And, okay, thanks so much. So we'll take a break, and we'll be back. Hi everyone. So I got the limit fixed, but not always it works dynamically on the meeting. So I was advised to just turn off the meeting and start it again. And so I'll turn it off and I'll start it in 7-8 minutes. And by then the 300 limit should be gone. Okay, so I'll close this off. Okay, please rejoin. The same link is fine.